So now let's learn a little bit about combinatorics, which is sort of a math subject, but it's commonly applied to coding interviews, usually for backtracking problems. One pretty common one is subsets. So we'll be going over how to understand these types of problems for coding interviews, but also a bit of math background that I think can really help you a lot. At least it's the reason I think that these types of problems are usually pretty trivial for me. So subsets is the simplest one. We'll also be going over combinations and permutations. But to start with subsets, suppose we're given a list of distinct numbers. That's important here. And we want to return all possible distinct subsets. First of all, what is a subset? Well, you have, these values. Well, a subset is pretty straightforward. It's basically any subset of these values. So, just the first value is a subset, the second value is a subset, the third is a subset, even 0 values is technically a subset. So if we just choose none of these, that counts as a subset of this set of numbers. We could take, just 2 values or these 2 or even all 3. That's pretty much every single subset. And we also want them to be distinct. So basically that would mean if we have a subset, suppose 1, 2, that we can't include a subset that is 2, 1. Just because the orders are different doesn't mean they're different subsets. That would be a permutation, but we don't care about permutations. We care about subsets, and these are technically the same subsets, so we would not include them. But since we're given a list of distinct numbers, we don't really have to worry about getting duplicate subsets. If we had, maybe an extra 3 over here, then we could potentially run into a case where, this is a subset. So that's 2, 3. And maybe just these 2 is a subset, but that's the same subset. It's 2, 3. So we wouldn't be able to include that. But for now, we don't have to worry about that. And for every subset, let's assume that the order does not matter. We talked about how these 2 subsets are technically the exact same subset. So which one of these would we return as a part of our result? Well, it doesn't really matter. Let's assume that for this problem, we can return either one. So this one would work or this one would work, but we can't return both of them, of course. So this problem is mostly straightforward if you're already familiar with backtracking and you have a basic understanding of subsets and the math in general behind them. Basically, for every one of these values, we have a choice. We can either include it in our subset or not include it in our subset. Does that sound like a decision tree to you? Because it does to me. So for the first position, we'd have, let's say, a pointer, I. We're going to be here. We can choose to include that value 1 or not include that value 1, which would leave us with an empty set. And then when we shift our pointer and we get to the next position, we have the exact same decision. We can either include this 2 in our subset or not include the 2. Basically, what we're trying to do here is create all possible subsets. It's not super complicated. We're in this decision including the 2, so we would basically append the 2 to our list. And this decision, we are skipping the 2. So we just keep that 1. Same decisions over here, but they're going to result in different subsets because on this path, we chose not to include the 1. So these are going to be all the subsets without a 1. These are going to be all the subsets with a 1. So over here, we would skip the 2. And then finally, we have one last decision as we get to the last index. Here, we can include the 3 or not include the 3. And over here, same thing. If we include the 3, we get the 1, 3 subset. Here, we can skip it. So you can see each of these subsets is unique so far, and it has to be the case because every time we branch, we're guaranteeing that they're going to be different because these are going to be all the subsets that included a 2, and these are going to be the ones that did not include a 2. So of course, all of the children are going to be different. We're going to quickly finish up the rest of this tree. Over here, we'd have 2, 3. Over here, we just have 2, running out of space a bit, but let's have 2 more decisions over here. And here we would include the 3. Here we would skip the 3. So you can see that this path is basically where we skipped every single one of these values. But that's important because remember, an empty set does count as a distinct subset that we're trying to return. So let's count the results. We have 1, 2, 3, 4, 5, 6, 7, 8. And that makes sense because remember, we started at the root, right? Just a single position, but we multiplied by 2 every single time because we're branching 2 times. So here we had 2 sets because we just had a single value. Here we multiplied that by 2 and we had 4 sets. And then finally at the bottom, we multiply by 2 again and we have 8 sets. So the number of subsets that we're going to have is always going to be the same. It's going to be 2 to the power of n, where n is the number of input values. Because remember, for each one of these, we have a choice. We can either include it or not include it. That gives us 2 choices. Same decision here, 2 choices. Same decision here, 2 choices. So 2 times 2 times 2 is, of course, going to eventually be 2 to the power of n, depending on how many values are in the input. So does that mean that that's also the time complexity, because this is how many subsets we have to generate? Well, not quite, because look, for every single subset, we're going to have to build it. Like, these are going to be separate arrays. We can't just reuse the work we did over here, because our result is basically going to be a big list, and these are going to be the sub lists. So we're going to have a nested array, and each of these children are going to be separate. So each of them are going to have to be built separately. So let's say, you know, this one is of course size n. Most of them are going to be smaller than size n, but we're going to approximate that each of them is of size n. That's like the worst case here. So if there's this many of these arrays and each one is of size n, then the overall time complexity is going to be n times 2 to the power of n. That's going to be the big O time complexity. When it comes to memory complexity, that is technically the exact same, because that's going to be the result. This is going to be the space it takes to contain this result. But typically, when we're talking about big O space complexity, we don't include the space it takes for the result. So if we're not including that, the space complexity here would be the height of the tree, which is in this case going to be n. So we would say the space complexity would probably just be big O of n here. So this isn't super crazy if you're familiar with backtracking. And if you're not, hopefully this makes sense, because this type of pattern is pretty common in backtracking. I mean, sometimes you'll have more than 2 choices, but it's all about the choices here. Let's take a look at how we would implement this with code. So this is one way to implement the code. So suppose that this is the function, like this is the one that's actually going to build the subsets and return them. So we're given just the list of numbers. Well, we're going to do this recursively with backtracking. That's the easiest way to implement this. So that's going to be our helper function. We're going to pass in 0 as the starting index. That makes sense, because of course, you know, we're going to start at the beginning here and then keep making decisions. We're going to pass in the nums array to our helper, but we're also going to pass in a couple helper variables. One is subsets. This is going to contain the result. So like, these are the subsets that we're building. This is an array, but each item in it is going to be a sublist. Like for example, 1, 2 is a subset, 2, 3 is a subset. These are the individual subsets we're going to be adding to the list of subsets. And the reason we're declaring it here as like an array and then passing it into helper is because for the scope of helper, like that can be considered kind of a global variable. So if we update it, like for example here where we're updating that subsets list, the updates will be reflected for the variable, because it's a reference to the exact same variable. It's not like we're creating a new array every time we call the helper function. It's the exact same array. We're passing in the same reference to that subsets array. We're also passing in another helper array, current set. So that's going to be a variable that actually helps us build an individual subset. So initially it's empty. So we start our helper function, assuming we start at index 0. We're going to check, are we out of bounds or have we reached the end? Because of course, when our I pointer is over here, that's how you know we're done. But assuming we haven't done that, we have 2 decisions to make, right? One decision is we include the number at index I. The second decision is we don't include the number at index I. So this is a standard backtracking template. Here, what we're going to do is to our current set, right? We're going to make the decision to include nums of I. So to our current set, like this is our current set, we're going to add 1 to it. And then we're going to call our helper function with the exact same variables, essentially, right? Nums isn't changing. Current set, well, that did change. We appended a value to it, but we're passing in the same reference, right? It's just a single variable, and we're reusing it throughout this recursion. We're also passing in subsets. And then after we called this recursively, like we know here, this is going to do a bunch of recursion. We're going to make more decisions here. We're going to potentially update the result with some base cases, but eventually we're going to be finished with this recursion, right? After this returns, After that, we want to pop the value that we just added here, because now we want to go down the other path where we decide not to include nums of I. And going down that path, we would want our current set to be empty, or at least we wouldn't want to include this value that we just added. So that's what we do. We undo the work that we did previously, and we do, basically this is called a cleanup, and then we go recursive again. You can see that these two recursive calls are the exact same. So what's different about them? Well, of course, the current set. The difference is on the first recursive call, the current set had the 1 added to it. On the second call, it did not have the 1. So this one is going to calculate all subsets that include 1. This recursive call is going to calculate all subsets that don't include 1. Now, for any particular ones, suppose we went down this path, we add a 1, 2, and then we have 2 decisions and we choose. Of course, we're going to go through all of them, but I'm just showing an individual one. Suppose we went down here and then we did not include the 3. And then after this, we basically go out of bounds, right? Our I pointer is going to be over here. We're out of bounds. That's when the base case is going to execute if I is greater than or equal to the length. Technically, this could have just been if I is equal to the length, because that means we're exactly out of bounds. If we go out of bounds here, we're never going to increment it farther. So that's why you could have just had this as equals, but there's nothing wrong with doing it this way either. But when that's the case, we reach the base case. Of course, we just want to take this helper array and then append it to our overall result. Like this is our overall subsets result. We want to take this 1, 2 and add it. But we know that current set is an array and we're passing in the same reference to every recursive call. So if we take this and add it to the result, and then, we pop back up potentially, and we pop back up again. Eventually, we remove the 1 and the 2. Well, that's going to end up updating this as well. If we remove 1 from here, we're going to end up removing it from here. So what we actually want to do is not add the exact same reference to this array, but we want to create a copy of this array. So that's what we're doing here. We're creating a copy of the current set before we add it to the subsets result. And then after that, we're just returning. So this helper function is not actually returning anything. What it's doing is it's modifying the subsets array that we have declared up here, and it's adding each individual subset to it so that after we've executed that recursive function, then we can go ahead and just return the subsets. So these are the main ideas. This is definitely not super easy, especially when you're new to backtracking, but getting a really good understanding of this can make future more difficult backtracking problems a lot easier, because they generally do follow this similar template. But there's a slight variation we can make to this problem. This is subsets without duplicates in the input array. What would happen if we did have some duplicates in the input array? Let me show you what we could do to fix that. So if we slightly change the problem and say that we're given a list of nums that are not necessarily distinct and we want to return all distinct subsets, how would we do that? So suppose we're given an array like this where we have 2 occurrences of the value 2. Well, the first thing we pretty much always do with a problem like this, and sometimes it's not even a backtracking problem, but usually with backtracking problems this applies, is we want to sort the input array. Because first of all, we already know that the solution to generate all distinct subsets is going to be exponential. So sorting, which is n log n, is not going to be super expensive, and it makes these problems a lot easier. And in this case, it's very important to solve this efficiently. We're going to sort the array, and you're going to see why I'm doing that in a minute. After the array is sorted, the problem is pretty similar to the original subsets, but let me just show you a problem that would occur. If we try the regular way of subsets, we have 1, and then we choose, an empty array here. Going down another path, we choose 1, 2. Here we stay with 1. Going down here, we choose 1, 2, 2. Going down here, we skip the second 2 over here, so we're left with just a 1, 2. Here, we choose the second 2, because that's where we're at here. We'll choose the second 2, 1, 2, and here we'll skip the second 2, so we'll just have a 1. Notice how we have duplicates here. At this point, this is not a base case. We still have some values left, but these two are going to obviously be the exact same because they're at the same position and they're going to make the exact same decision. So these two paths are going to result in duplicate solutions, that we're going to have duplicate subsets in our result. That's not what we want to do. So we can't, use the same idea that we had where for every single number, we choose whether we want to include it or not. Because if we make that decision here, we include this 2 or not, or we make that same decision here, we include this 2 or not, that's not necessarily going to result in distinct subsets. Logically, what we really want to do is have a path, for example, where we say, okay, this path is going to have 2 occurrences of 2. And this path is going to have 1 occurrence of 2. And maybe a third path is going to have 0 occurrences of 2. So we don't include either of these. So those 3 paths would definitely not result in distinct subsets. So that's what we're going to do logically speaking. We're just going to implement it in a different way. We're going to take advantage of the fact that this array is sorted. So let me show you what I'm going to do. For the first value, we're going to make the same decision because since this array is sorted, we know that all duplicates are going to be adjacent to each other. So we'll be able to tell that there's only a single 1. And when we get to 2, we'll be able to tell that there are multiple 2s. So here, we're going to, for the first value, make the same decision. We have a 1 or we have an empty array so far. We're going to get to the second position here, and we're going to make a similar decision. So here, we're going to choose to include the 2. So we'd have 1, 2. Here we're going to choose to not include the 2, so we're just going to have a 1. So this is going to be the path where we not only skip the first 2, but we're actually going to skip both of these 2s, and the next time we make a decision here, we're already going to be at this position. So here, we're going to make the decision, do we include the 3 or do we skip the 3? What we're trying to do is we want this path to represent all subsets that don't include any 2s. So what about this path? Is this path going to include both of the 2s? Not necessarily, but clearly it's going to contain at least 1 2. So we know it's going to be distinct from this side. This is not going to generate any duplicate subsets that this one will. And of course, we know that this right side is not going to generate any duplicate subsets with this path because this is not going to include the 1, whereas this does already include the 1. That's why I'm kind of just glossing over this part. But to focus back here, where the duplicates actually occur, here we have 2 more decisions now. We're at the second 2 over here. We can choose to include the second 2, where we would have 1, 2, 2, and here we can choose to not include the second 2 where we just have a single 2. So now you probably get the idea. This is the path that does not include any of the 2s. This is the path that only includes a single 2. We don't care if it's the first 2 or the second 2 because it doesn't really matter to us. This is the path that includes a single 2. This is the path that includes both 2s. So we clearly know that these 3 paths are always going to be distinct. How did we accomplish this? It's because it's pretty clever. Well, from up here, we basically said this is the path that's going to include 1 or more 2s. So if we know this is the path that's including 1 or more 2s, then this is the path that can't include any 2s. So what we did here is when we skipped this spot, we didn't just skip the first 2. We just kept skipping while the neighbors were the same value. So if there were even more 2s over here, if this was a 2, we would have skipped this one and we would have skipped this one. We just keep skipping while the values are duplicate. At least that's the case when we go down this path. And by the way, if we did have extra 2s, like for the example, this one and maybe even more, the same logic would be applied to these children as well. So here where we include to maybe include that third 2, that's great. But here where we choose to skip that 2, we'd not only skip this 2, we'd skip all the 2s. We'd basically skip until we got to a new value. That's to ensure that, these don't end up resulting in duplicates either. So that's the main idea. So it's very similar to the first subset problem, but it's definitely not the type of thing you could easily come up with by yourself. So it's very helpful to have seen this before. It's definitely a common pattern that can come up in a lot of backtracking problems. Let's take a look at the code now. So time complexity and space complexity wise, it is the same, because in the worst case, we wouldn't have any duplicates and then we'd have 2 branches every single time. We wouldn't have to skip any values. So, the size of the tree would be to the power of n. For each subset, it takes n to build it. So that's the time complexity, and space complexity would again just be the height of the tree, which is big O of n. And you can see the first thing we're doing before we do anything is sorting the input array. That's very important because we're not guaranteed that the input array is going to be in sorted order. Other than that, code-wise, it's pretty similar. We have that subsets list and we have the current set list. We're passing those in. We're passing in nums. We're starting at index 0. And then eventually, once we've built subsets, that's what we're going to return. But how do we actually build it? Well, this is also pretty similar to the first one. If we reach the end of the list, we're going to take our current set, create a copy of it, and append it to our subsets and then return. Otherwise, we have 2 decisions to make, the exact same decisions. We can either include this number, so we would append it to our current set, call our helper recursive function i+1, and then we'd pop that value and basically make the decision to not include nums of I. But how are we going to do it? This is where it gets a little bit more tricky than the first solution, because we actually have a while loop here. The first solution we could do without any loops. This one is helpful to have a loop. Basically, we're going to make sure I+1 is out of bounds. That just means we're not at the last value. So for example, let's say we're over here at the first 2. We're going to check, is the value at this index equal to the value at I+1? Are these 2 guys equal? If that's the case, we're going to increment our I, because remember, we're trying to skip nums of I. Our I pointer is here. We're trying to skip 2. So if we call our recursive helper function on I+1, which would be this, we would not be skipping 2 at all, because we're trying to skip this and we get to another 2 here. Well, we want to skip all these 2s, so we're going to increment our I pointer 1 more time. So now our I pointer would be over here. It's still at the 2, but that's okay, because at this point our code would say, well, I is still in bounds. Well, I+1 is still in bounds. I+1 is over here, but nums of I, which is here, is not equal to I+1, which is 3. So that's okay. And that's because when we call our helper function, remember, we're not passing in I, we're passing in I+1. So even though our I pointer is over here, we would pass I+1. So we would start our recursive function at 3. So that's what we're trying to do. When we reach duplicate values, we want to skip all of them when we, go down this path at least. Other than that, it's pretty much the exact same as the first solution. So I hope I was able to demystify something that can trip a lot of people up. These type of problems are definitely not trivial when you're first learning them, but after a while, they do start to make sense. They definitely follow a very similar pattern.